In this exercise, we would like to do the conversion for the 76, which is in decimal, and convert it to hexadecimal and binary. Then, we need to deduce the rest of the conversions from the first line. In order to proceed, let's first convert the 76 to a hexadecimal. If we divide the 76 by 16, the nearest number will be around 4. The remainder is 12. So the hexadecimal can be written as the 12 is equivalent, according to the table, to letter C. We can also use the table in order to convert this to binary straight away. The letter C is equivalent to 0011, and the number 4 is equivalent to 0010. Now we need to convert the 38 to hexadecimal and binary. However, we need to do this by deducing the values from the previous line. We need to find a relation between the 76 and 38. And if you notice that the 38 is actually 76 divided by 2. So 76 divided by 38 is actually 2. In computers, the division algorithm involves conditional shift to the right and subtraction, whereas in multiplication, it involves conditional shift to the left and addition. In simple cases, when we are dividing or multiplying by 2 to the power n, where n is 1 here, then we simply can shift the binary by 1. Because we are dividing, then we are shifting it to the right by 1. So in this case, the binary equivalence to 38 is actually the same binary for 76 shifted by 1 position to the right. So this leads to the following number. We added 0 to the left in order to complete the 8-bit representation. Now we can convert this straight away to hexadecimal by looking at the first half byte, which is a 0110, which is equivalent to number 6. And if we look at the other one, which is 0100, this is equivalent to 2. So keep in mind, when we are dividing by 2 to power n, then we need to shift by, we shift to the right by n positions. Now n here is actually the exponent of 2. And we're shifting right because we are dividing. Let's take the other example of 152. We notice that the 76 is multiplied by 2 in order to get the 152. So multiplying by 2, or 2 to power 1, means we have to shift left by 1 position. So 76 multiplied by 2 to power 1 is 152. Because this 1, which is the n position, and because we are using multiplication, then we shift to the left by 1. So n here is actually 1. Going back to the same binary representation, we need to shift this left by 1. This will give us the following number: 1, 0, 0, 1, 1, 0, 0, and then we have to add the extra 0. So we have just shifted to the left by 1 position. Let's look at the last case where we have 304. 76 is multiplied by 4, which is 2 to the power 2. And because we are involved in multiplication, we have to shift to the left. Now, because of the exponent of 2 is 2, then we have to shift to the left by 2 positions. So 76 multiplied by 4 is 304. This means we shift to the left because of the multiplication by n positions, but now n is actually equals to 2. So let's get on and shift the representation of 76 by 2 positions to the left. This means we are adding 2 zeros on the right hand side. We forgot to put the hexadecimal representation for the previous one. The 1000 is actually 8. The 1001 is 9. And we only have an extra 0, which can be represented as 0. For the last line, this can be also converted in a similar fashion to the hexadecimal number. If we look at the first semi-octet, it's a 4 zeros, so that's 0. Then we have 1100. This is number 3. And we have 10, which is equivalent to 1000. That's 1. In summary, we can write the following. If you divide by 2 to the power n, this is equivalent to the shift to the right by n positions. And if you multiply by 2 to the power n, you are shifting left by the n positions.